Hi, and welcome to lecture number 4. Today we'll talk about invariant measures, and we will finally get to understand what the ergodic decomposition is. So recall from the previous lecture that we saw that if you have a convex compact set, we call it M in Rn, then this set has extremal point. The set of extremal point was called E, and every point in the set M is a convex combination of points of E. What it means is this: if you take some point x in M, then there exist extremal points xi, finite set of them, let's say M, and positive or non-negative numbers pi, whose sum is 1. So pi, you can think of as probabilities, so that x equals the sum pi times xi, the weighted average of the points xi, if you want to call it that way, or the center of mass. Now, if you want to make things look much more complicated, then you can say that there is a probability measure defined on the extremal points only, so that when you integrate the set of extremal points, here is the integral goes on nu, and nu is a point varies over the extremal set E. Then this integral gives you the point x. Of course, the probability measure lambda is not a very interesting one. All that we get from the probability lambda is that it gives weight pi to the point that in the previous discussion was called xi. Now there is a generalization of this to the infinite dimensional setting, which we will particularly interested in when we talk about Cx star. It's called Choquet's theorem. This is actually a relatively simple case because Cx star is a metric topological space with a weak star topology, and as such it's a metric space. We saw that last time. But it's more general than this, and for certain topological vector spaces, what Choquet proved is that if you have a compact convex set inside this metric space, then exactly like what we've seen in the finite dimensional case, every point in M is an average of extremal points. But this time we have to use the more complicated looking definition of average. There is some probability measure lambda on the sigma algebra of extremal point x, so that the integral over the extremal point with respect to this probability measure lambda, gives us the point x. So again, x is the center of mass of extremal points if the extremal set is endowed with this particular probability measure. Of course, it makes sense here to say Borel sigma algebra because Cx star is a topological space and D is a subspace of it. And just to be sure that we are understanding the notation the same way, when you write d lambda of nu, it's just to emphasize that the name of the point nu is the name of the point that ranges on the extremal set E. In the literature, you will sometimes see this as an integral over M instead of over E, where M is whatever your compact convex set is. But then it says that the integral is supported on E, which means M minus E has measure 0. So it's the same thing really. We will later apply it to the space that we called M sub t. M sub t is the space of invariant measures, but we are not yet ready to discuss. So before getting into any kind of discussion about M sub t, we want to get into a more elementary discussion. We just said that a point in the convex set M, the compact convex set N, is an average or center of mass of extremal points. So what does it even mean to say that you have an average of measures? To understand that, let's start with x bx, which is going to be actually later exactly the metric space x that we were discussing, which is just a measurable space, but in particular it doesn't have any specific measure on it. Y, which has a priori nothing to do with x, is a probability space. So it has its own sigma algebra, let's call it by, and more importantly, it has a probability measure lambda. So we can average y by taking the integral over all points of y d lambda. And now supposing that we are in the setting that every point of y is in fact a probability measure of x. So we're in exactly the setting that we want, that we have some parameter space, if you want to call it that, y, that parameterizes all the probability measures that we want to look at. It doesn't have to be all the probability measures at all in the world, but all the ones that we are interested in. And then we can average points of y the way we always have. We can write the integral over y of nu d lambda nu. That's exactly what we had on the previous slide. And this time we're going to say, because each one of the nu's is itself a probability measure on x, we're going to call this mu sub x and claim that mu sub x is a measure on x. And my goal in this particular slide is to make sense of this statement. Mu sub x is a measure of x. What does that mean? Well, we need to see what the measure is. So given a measurable set E, and this is E in Bx, it's a measurable set in X, we define mu sub x of E to be the integral over y, this is the blue integral here, of mu sub E d lambda y. So we are averaging now numbers. Mu sub E is just the measure of E, so it's a number, and we're taking the average of mu sub E when the average is some sort of a weighted average, and the weights are given by lambda. Of course, what actually happens here is that when given a measurable set E, it defines for us a function from 1 to r, y to r, and that function is given by E of nu. Nu is a point of y, is just nu of E. The blue integral here, we simply integrate this function. Now, another thing that we can do with a measure is integrate functions. This is more general than just asking what is the measure of a set. So, given a function from x to c, if I have a measure on x, I need to be able to make sense of the integral of x d mu. And the way we understand it is the integral of y d lambda y, where the quantity that we integrate is the integral of x over x of the function f d nu. Remember that nu, as a point of y, is a probability measure on x, and so the inside integral makes sense. This is in fact more general than what happens in this case over here, because if I take for f the indicator function of E, then this integral inside here, the integral of x of the indicator function of E d nu, is just the nu measure of E, and this integral over here, that's just the mu measure of E. And of course what happens here is that f now defines again a function from y to r given by, well, if you give me a point in y that's a measure of x, I'll get a number in r. I should have said a number in c, in fact. Oh, what do you know? This is actually c. How'd that happen? So we have a function from y to c, which is given simply by taking the function f and integrating it over the entire space x, d measure nu. And what we do with this function, again, the blue integral here is just integrating this function over the entire space y. So that's how we understand average of measures and why the average of measure is itself a measure. And of course, it's an easy exercise to see that it's a probability measure. You integrate the function 1 and you will get the average of 1s, which is 1. Now, an invariant measure, let us write down the definition explicitly once and for all, is given when you have a compact metric space x d as before and a continuous transformation t from x to x. Of course, being continuous, it's automatically measurable with respect to the Borel sigma algebra. And then a measure mu, a probability measure on x, is called invariant if the transformation becomes an invariant transformation if we use mu as our measure on the space x. That is to say, for any measurable set E, I want the mu measure of E to be the mu measure of the preimage of E under T. The set of all invariant measure transformation is called M sub T, and this is a subspace of M sub x, and as such it inherits a topology and all that good stuff. Now we saw before that M sub x is compact, convex, and non-empty. This was all pretty easy except for compactness. For compactness we had to work. We claim that M sub t is also compact, convex, and non-empty. This is all pretty easy. This time the exception is the non-emptiness. To see convexity is very easy exercise, which I will leave for you. Compactness follows from compactness of M sub x as soon as you show that M sub t is non-empty. So the main issue with this whole line of argument is showing that there actually is an invariant measure. So let's start with mu, a probability measure of n sub x of your choosing. Recall that m sub x is not empty. For instance, you can take the measure that gives 1 to any measurable set that contain a specific point x in it and 0 otherwise. Well, mu, of course, is a function from the Borel measurable set to R. For any positive number r, if we apply t inverse I times, this gives us a function from the Borel sigma algebra to itself. That is simply because t to the I is measurable, and we get a new function by composition. This function is very easy to describe. It simply says that the measure of a set E is the measure of E, of the preimage of E under t to the I. Okay, now given any number greater than or equal to 1, we can set mu n to be the average of the measures which are obtained in this way by applying t. I times I goes from 1 to n minus 1. So this is n measures, mu, t inverse mu, t to the minus 2 mu, etc. And we take their average. We know that mu sub x is compact. And that means that, is of course not mu sub x that is compact. It is m sub x that is compact. At any rate, m sub x is compact, which means that the sequence that we find here must admit a convergent subsequence, and the convergent subsequence converges to a measure which we can call mu infinity. We're now ready to state what is known as the Krylov-Bogolyubov theorem, which is very easy to state. M sub t is non-empty. And how do we prove that? Well, the claim is that the measure mu infinity that we just obtained a moment ago is the invariant measure. So let's look at the measure mu sub ni, and what that does, how close is that to being invariant. If we apply mu sub ni to some measurable set E, and we subtract from that mu sub ni applied to the preimage of E, well, mu sub ni is the average of mu sub E, mu plus mu sub t, and mu sub t inverse of E, mu sub t to the minus 2 of E, and so on, all the way to mu sub t to the minus n plus 1. Similarly, mu sub ni when applied to t to the minus 1 of E is an average of mu of t to the minus 1 of E to the minus 2 of E, and since we apply t inverse one more time, the last set that we'll see here is t to the minus n of E. So the average, 1 over ni as a common factor, comes out. The only thing left from here after cancelling is mu of E. The only thing left from here after cancelling is mu of t to the minus n of E. Everything else cancels between these two. This is the difference of two numbers. Each one is somewhere between 0 and 1. The difference cannot be more than 1. And we see that the difference between the measure mu sub n of E and the measure mu sub n of t inverse of E is indeed very small as ni becomes very big. Taking the limit, we see that the difference between mu infinity of E and mu infinity of t inverse of E is in fact 0, and that's what we wanted to prove. Mu infinity is an invariant measure, and therefore the set of all invariant measures is non-empty. This is actually it for proving that there is an invariant measure, but later on we will need to be a little bit more careful with how we choose the invariant measure. We can't be careful with how we choose the original measure mu. We just have to say some measure, probability measure that exists. But we can be more careful with how they choose the sequence of measures that converge. So suppose that we pick two sequences of integers, ni and mi, with the property that ni is bigger than mi, and as you see down here, it's much bigger than mi, and mi is non-negative. I want the limit of ni minus mi to be infinity. In other words, we're choosing interval of integers. Each interval starts with, the ith interval starts with a point that's called mi. It goes mi plus 1, mi plus 2, all the way to ni minus 1. It has length ni minus mi, and I want that to be arbitrarily large. Again, we can define a sequence of measures called mu I, which is again just the average of the measure mu composed with t to the minus I, but this time I ranges on a chosen interval from mi to ni minus 1. The exact same argument that we saw before tells us this mi has a convergent subsequence that's just the compactness of m sub x, and the limit is an invariant measure. All we needed in order to see that the limit is an invariant measure is to know that we are averaging over longer and longer intervals. So when we take the measure of some set E and subtract from it the measure of the set T inverse of E, we have this factor here, 1 over ni to the ni minus mi, which is a giant number. When 1 over it becomes a tiny little number, and that's what tells us that in the limit the measure is indeed invariant. So this at this point doesn't help us because we already have an invariant measure, but the flexibility to choose these intervals, and in particular I can choose these long intervals not starting at 0. If they always start at 0, if mi always equals 0, this is exactly in the construction on the previous slide. But if I can start the intervals in other places, it turns out that this exact flexibility is useful. Now, before we go on to describe the ergodic decomposition, let's look at one example. So suppose that our space now x is simply the closed interval 0, 1, and we have a transformation t from 0, 1 to 0, 1, and I owe you a continuous transformation. T of x simply equals x squared. Of course, t has two fixed points, 0 and 1, and you immediately, when you have a fixed point, you automatically get an invariant measure, which is the measure that's concentrated at that one point. We have delta 0, which gives measure 0 to any set containing the point 0, and measure 1 to any set containing the point 0, and measure 0 to any other set. And the measure delta 1 similarly gives measure 1 to any set containing 1, and measure 0 to any other set. These are immediately invariant measures, and because they are invariant measures, any convex combination of the two will be an invariant measure as well. So if you pick a point P in the interval 0, 1, you get yourself an invariant measure mu sub P, which is just 1 minus P times mu sub 0 plus P times mu sub 1. And as an exercise, let me ask you to prove that there are no other invariant measures. If you want to think about how to prove that, take yourselves an open interval inside the closed interval 0, 1, but maybe not something that stretches all the way to 0, 1. Something like the open interval 1 over n to 1 minus 1 over n. Actually, open or closed, it doesn't matter. It's contained in the interval 0, 1 over n. It's contained in the interval 0 to 1 minus 1 over n. If you apply t many times, this interval will shrink to an interval 0 that's contained in 0, 1 over n. And from this you can conclude that the measure of the entire interval 1 over n to 1 minus 1 over n has to be 0. And then you know what happens when you take a countable union of measure 0 sets. So this gives us a complete analysis of m sub t of this specific transformation. There are two measures which are somehow more interesting than the rest, and all the rest are given by a linear combination of those. Note that it's a natural thing to say that the space of measure of the invariant transformation for this transformation t is itself a closed interval. That's where P lives. P lives in a closed interval, and the two measures that we singled out first, delta 0 and delta 1, were the extremal measures here. Okay, so we finished today's lecture, which was titled Invariant Measures because the main thing was proving that invariant measures exist, by applying Choquet's theorem now to the invariant measures m sub t. What do we know about the invariant measures m sub t? We know that m sub t is a compact, convex, and non-empty set. E sub t are the set of extremal invariant measures. Applying Choquet's theorem tells us that any point in M sub t is... I apologize. The fire alarm just went off in my house, which tells you never cook and record. Anyway, back to where we're talking about. If I apply Choquet's theorem to this convex compact set MT, we get the main result of this slide, which is called the ergodic decomposition theorem. Choquet's theorem tells us that any point of the compact convex set MT is the weighted average, or the center of mass, if you like, of extremal points, if, of course, you choose the weights correctly. And it's stated as follows. For any invariant measure in M sub t, there exists a probability measure lambda on the Borel sigma algebra of E sub t with the following property. Mu that we started with equals the integral over the extremal points of the measure of the extremal point nu with respect to this specific measure lambda. So what the ergodic decomposition tells us is not so much how to decompose the space, or whether we'll get to talk about that a little bit in the next lecture, but how to decompose the measure itself into very small components. Each one of them is an extremal measure. I'm saying very small component because in typical situation, ET will be an infinite set, and so the measure given to each specific nu is of course 0, but as is always the case, when you integrate with respect to a probability measure, you get some center of mass. So that's it for this recording, which was more eventful than was planned. And next time we will continue to discuss this specific theorem, the ergodic decomposition theorem, because the question that this brings out is, what does it actually mean if a measure is extremal? Goodbye for now.